Hello everybody, and we are now moving on to 4.2, and we're going to be talking today about how do you integrate the energy equations with momentum equations, okay? Again, as always, if you haven't started reading the textbook, please do so. It's Chapter 8 in Coletta. Momentum, Chapter 10, if you're in Physics 111, and not Chapter 10, homework 10, if you're in Physics 111. Homework 7 and 121 are related to this topic, okay? And we are going to be doing, when you do your labs, your virtual lab stuff, if you have the actual physical lab books, look in labs 10 and 11. All right. Well, energy and collisions. So essentially, here's the thing. Besides creating a momentum equation, you could also integrate energy equations in this. And specifically, since there's no potential energy due to gravity, there's no springs, there's no outside works or such as friction or thermal energy. Well, there might be thermal energy, but my point is we're just going to be looking, the only energy that is going to be needed to look at really is kinetic energy. And specifically comparing the kinetic energy before to the kinetic energy after, okay? And so what this is saying is this. I'm going to mark up this document to take a couple notes to illustrate what I am talking about. So what we learned before is since the total change in momentum is equal to 0, okay, such that the initial momentum is equal to the final momentum. Well, if there are no and the system is completely contained, meaning there's no external forces or internal forces leaving or exiting the system, leaving or entering the system, then the total change in momentum is 0, right? There is no J vector. Well, if the system is contained, has all the forces contained within it, what we could also say, and let me back up. Let me just back up what I was saying. Is this what I mean by there is no total J vector? Normally, when you sum up when you have the total change in momentum, that's equal to the impulse or force times time, right? Well, if all the forces are contained in the system, that is 0, meaning the initial momentum is equal to the final momentum. Well, when we're summing up these two objects are moving in the beginning, we learned that the work energy theorem is this, right? That the total work entering or exiting the system is equal to the total change in kinetic energy. Well, similarly, if all of the forces are contained within that system, then there is no work, external work entering the system or internal forces work leaving the system. So what that is saying also then is that the initial kinetic energy is equal to the final kinetic energy. So with elastic collisions, okay, and only with elastic collisions, both momentum and kinetic energy are conserved, okay? Because if basically everything is just being contained within that system. However, this is not the case with everything, okay? With all types of collisions, okay? So we just had worked out that elastic collisions, both the momentum and the kinetic energy are conserved, okay? However, there is an issue with inelastic collisions, right? When an object hits another object, again, the the initial momentum is equal to the final momentum. But what we're going to find out is that the initial kinetic energy is not equal to the final kinetic energy. When the two objects are colliding inelastically, they stick together, right? And when these two objects slap each other and they stick together, what you find out is that the initial kinetic energy is greater than the final kinetic energy with inelastic collisions. Okay, so there's a problem, right? So you could use two equations with inelastic collisions, momentum is conserved and kinetic energy being conserved, to solve for the velocities and other things with elastic collisions. But with inelastic collisions, since the final kinetic energy is less than the initial kinetic energy, and what that means is that delta K is not being conserved, meaning delta K is not equal to 0, it's actually equal to some energy, right? And that means there's some energy leaving the system. Okay. So we're going to use this stuff to analyze energy and also at momentum at the same time. What you end up finding out is that the percent of energy loss is actually due to the difference in masses, right? If you had just a object mass 1 coming in, so this is mass 1 coming in, it's got a velocity to the right, and it hits another mass 2, and we'll just say this mass 2 is not moving. Well, now, after that collision, the two objects are stuck together and moving with some final velocity. Well, what we find out is that this energy loss, this is an energy loss, is actually the amount of friction being lost in this system. Is actually due to a frictional change. There must be some kind of slap or an explosion, and I'm drawing little explosion lines around this. So there's an energy loss during this when these two objects hit each other. Okay. So to illustrate this, we're going to do a problem, and it's a really neat problem. We have it's from a lecture tutorial, but we're going to actually do it here. We have a bullet moving to the right, and the bullet has mass m. It's going to hit a block of wood that has a much greater mass than it, and it's going to get buried in that wood right here. And so now they'll both be moving together. So this is an inelastic collision, and then as they're moving along with this kinetic energy, they're going to hit a spring and be brought to a stop. Okay, so this is a complex problem. It starts with a momentum problem with an inelastic collision, and then it turns into a kinetic energy slash potential energy to a spring problem. Okay, so here's how to put all this together. Okay, so you have, and this is just in equation forms. So you have this bullet traveling with an initial velocity, and it's going to hit this piece of wood which is not moving. And then afterwards, the combined objects are going to be moving together. So it's got a mass, and this is a capital M, and now they're both moving together. Okay? And this is the momentum problem right here. So we're only going to use momentum during the initial and middle stages of this. On the next part, we're going to analyze the kinetic energy before and the kinetic energy in the middle stage, and compare that to the kinetic energy in the middle stage to the final stage, right? So it's going to be kind of cool. So this initial block has initial momentum, and this guy has no initial momentum. And then at the end, both of them are going to have a final momentum, right? So the bullet, let's just say the bullet has an initial momentum of 3 blocks, right? 3 blocks. Well, the block has no initial momentum, and in the final momentum, both the bullet and the block are going to have a combined final momentum that has to be equal to the initial momentum. And since we're not dealing with numbers, I'm just going to call this plus 3 blocks. That has to be equal to the final 3 momentum, which is also final 3 blocks, right? And so while momentum is always conserved in any collision, the kinetic energy, we know from what we just talked about, is not going to be conserved. We know that there is going to be some kinetic energy loss here. Okay? So let's go ahead and solve this like we regularly would. The problem is asking us to actually do this symbolically. So this is going to be the mass and the initial velocity of the block, and this is going to be the combined masses of both objects and their final velocity, right? So the initial momentum is going to be the momentum of the bullet plus the momentum of the wood. I'm still going to list that out, but then we know that is 0. And that's going to be equal to the momentum of the bullet plus the mass of the bullet plus the mass of the wood and their final velocity combined. Okay? So here we could actually find the final velocity. Let's just do it while we're here. And that's equal to this. Oh, where did I put the velocity there? It's the mass of the block. And so dividing both sides by that, we get the final velocity of both blocks together equal to this. Mass of the bullet. So it's momentum of the bullet, the initial momentum of the bullet, divided by the combined masses of both the block and the bullet is the final velocity. Alright? This is going to be important, right? This is going to help us later on with the energies. So we talked earlier that, again, that during an inelastic collision that the total kinetic energy is not conserved, meaning the initial kinetic energy is not equal to the final kinetic energy. So what I'm going to do is I'm going to go ahead and I am going to write that final velocity of both objects together. This is the momentum of the bullet plus the combined masses of the bullet and wood, right? So that's a representation of the final final velocity of both objects, right? Well, let's assume that the kinetic energies are conserved, right? Meaning that total energy in is equal to the total energy out, okay? And if the total energy in is represented by the kinetic energy of just the bullet and its initial velocity, and the energy of the block of wood in the beginning was 0 because it was not moving, right? And that should be equal to, after the impact, that should be equal to 1/2 m v final squared. Oh, and I should put both of those. I got to put the combined masses. Almost made a mistake of both objects, right? Well, if this works out and we solve for the final velocity, it should appear as this exact same equation, right? Because we know momentum is always conserved. Well, here's what I'm talking about. The 1/2s are going to cancel out, and so let me not do that. The 1/2 is going to cancel out with this side, and what you'll have is mvi squared equals m plus capital M, mass of the bullet, mass of the block of wood, v final squared. And divide both sides by that, vi squared over small m plus capital M equals v final squared. And what that means is is that final velocity we're going to square root both sides, is equal to vi squared mvi squared over small m plus capital M, which is going to be equal to vi square root of small m over little m plus capital M. This value right here, this value right here is not equal to this value. In fact, we could for sure say this, MVI, this is the equation created from our momentum stuff, is greater than this. And I know I did that with equation-wise. And I wanted to do this to illustrate this. This is the bullet. This is a block of wood. This is the bullet. This is a block of wood. So let's say it had 3 blocks of kinetic energy coming in. Well, what that means is now it's lost some energy, right? Because this right here, and let me back up. Let me rewrite this equation so it looks a little bit different but means the same thing, is VI, and this is M over small m plus capital M. So what I'm saying is these two things are not equal. This guy, the one obtained from the momentum method, has more final velocity. Okay, this is the final velocity here, okay, from the momentum method, than this guy, right? So that means we've lost energy. If it started out with 3 blocks of wood and now it has 1 block of wood and it hasn't even touched the spring yet, that means energy had to have left the system, right? That means it had 3 blocks of wood minus 1 block, that's going to be, 3 blocks of wood, 3 blocks of energy minus 1 block is going to be equal to 2 blocks. That means there was energy leaving, and that's usually done in terms of thermal energy or some type of work leaving the system. Okay? So my point is that you cannot use conservation of energy to solve a problem with inelastic collisions for a collision process. But what you can do is use the momentum stuff that we did earlier to get the velocity of the object. And once the collision has occurred, now you could use that stuff, that velocity, okay, because that's a reliable velocity, to analyze the problem there on out. So basically, while the initial energy is not equal to the middle energy, what you can say is that the middle energy, being 2 blocks of wood, now that if we solve this kinetic energy of this, and it is 2 blocks of wood, right, then that is going to be equal to the final energy, right? Actually, it'll be 3 blocks. So I guess let me illustrate this. So if suppose we say that during the middle energy now, it's got a kinetic energy, right? The 2 block system right here has it's going to be 1/2 the combined masses, and it's going to be their final velocity squared. Well, where does that final velocity come from? Well, we could use the final velocity from the momentum problem, which is going to be MVI over M plus capital M. We know that that is a reliable final velocity, and that is obtained from doing the momentum. Because what we know is that the momentum is always conserved. So we got this equation for the velocity from the momentum part, right? So now it's got kinetic energy, and we're going to call it 3 blocks of kinetic energy, and that's 3 blocks of kinetic energy. And the spring is going to bring it to a stop. So the spring is going to do work and bring it to a stop. And this is going to be equal to 1/2 kx squared. So the only time in inelastic collisions you could use energy for a problem with inelastic collision is only before or after the collision. You can't use kinetic energy to solve for this during the collision process because energy gets lost, right? This final velocity is not equal to the final velocity obtained using the momentum method. Okay, this is the momentum method. I should say this is from the momentum, and this is the kinetic energy stuff. So the kinetic energy, analyzing the kinetic energy during a collision is unreliable for inelastic collisions. Okay? So this is kind of how you do energy problems when energy is, with momentum problems, when energy is not conserved due to an inelastic collision. With an elastic collision, had we worked this out with an elastic collision, then this equation would have worked out to be the same thing as this. And then the 3 kinetic energy would be equal to the 3 kinetic energy here, and we wouldn't have to worry about that. Okay? But in this case, the energy is lost. Okay? Well, what I want you to do is go on and do your lecture tutorials. Okay? Do your lecture tutorials. And do the lab associated with this, and then do the sapling homework. Okay? I hope you had a good time. See you next time.